Hello everyone, this is Aditya and today we'll discuss how to prove pi square by 6 is equal to 1 plus 1 by 2 square plus 1 by 3 square and so on and so forth. And we all know that it was derived by Euler, and let's see that how we can derive it. So in this video, I'll be using the method of Fourier series to prove this expression. So let's see how we will do it, okay? And yeah, I will make a one shot on Fourier series soon, so please wait for that. And before that, we will solve this question, how to prove it. Okay, so we all know that f at x, there are some conditions for the function to be expressed in the Fourier series, but we won't discuss about them right now, is equal to a naught by 2 plus the summation as n goes from 1 to infinity of an cos nx plus bn sin nx. We all know this, okay? So there are some relations between a naught and fx, an and fx, and bn and fx, and using those things we will derive certain functions for an, that how they vary according to the value of the function and other things. We will see it, okay? So we all know that a naught over here is equal to 1 upon pi, and yeah, here x varies from negative pi to pi, okay? So now let's see, a naught is equal to 1 upon pi integral 0 negative pi to pi of fx, let me write it clearly, dx, okay? An is equal to 1 upon pi integral negative pi to pi of the quantity fx into this function, and bn is equal to 1 upon pi integral negative pi to pi of the quantity fx sin nx dx, okay? So using these relations, we will figure out the value of a naught, an, and bn, okay? So let's see how we will solve it. So let's assume that our function is fx is equal to x square, and we will do our calculations for fx is equal to x square. So let's find the Fourier series for x square and let's see how it goes, okay? So let me erase this and we will be right back. So let me write all the expressions over here, and then we are going to start. Fx is equal to a naught by 2 plus the summation as n goes from 1 to infinity an cos nx plus bn sin nx, right? This is the expression for the Fourier series, and we know that a naught is equal to negative pi 1 upon pi negative pi to pi of the quantity fx dx, and an is equal to 1 upon pi integral negative pi to pi of the quantity fx cos nx, right, dx. Of course our dx is important, and bn is equal to 1 upon pi integral negative pi to pi of fx sin nx dx. And in our case we find the Fourier series. We are finding the Fourier series. We are finding the Fourier series for fx is equal to x square, and in the range of negative pi to pi. We are calculating in this range, okay? So let's solve. So let's see. So let's substitute fx as x square. Notice that fx is an even function, right? So it will help me in our calculation a lot. And when I will take the one shot of the Fourier series, I will discuss that how the things goes when the function is even, when the function is odd, when it is half sign or whatever. We will see all that, okay? No need to worry about that. So basically a naught is equal to 1 upon pi integral negative pi to pi fx dx, but we have assumed that fx is equal to x square, so we will put the value of the function over here, and we get 1 upon pi integral negative pi to pi x square dx. Well, it is not important right now, but like you all can evaluate this is a very simple integral, but to tell the concept I'm telling it. We all know that this is an even function, so in the case of an even function fx dx, where fx is even, what do I mean by even function? Suppose f at negative x is equal to fx for all x, then in that case we say that such function is an even function. And when f of negative x is equal to negative f of x, then we say that this is an odd function. And if a function satisfies such properties, then it has a very significant effect on an integral. Let's see how. So if fx is even in this case, it will be equal to 2 times the integral 0 to a fx dx, but ultimately you have to evaluate the integral, okay? But if it is a odd function, negative a to a fx dx, and notice the limits are from the same quantity, the negative of the same quantity to the positive of the same quantity, and fx is equal to a odd function, so it will be equal to 0, and in such cases the calculations reduce significantly, and we will see how. Okay, let me erase all this, and we will be right back. Okay, now let's evaluate this. Let me put a box over here so that the things don't mix, right? Okay, so you can write this as 2 by pi means 2 times this quantity, negative from 0 to pi x square dx, and it is a very simple integral. You all can evaluate it. X cube by 3, you substitute the limit 0 to pi. When you substitute 0, the value becomes 0, and when you substitute pi, it becomes pi cube. Pi cube by 3 minus 0, we don't need to write, is equal to 2 pi square by 3, right? So we have got the value of a naught. Let me write it over here. So a naught is equal to 2 by 3 pi square, right? Okay. Now similarly, let's evaluate for bn first of all, because I have to tell the concept over here. So bn, we all know that bn is given by a relation 1 upon pi integral negative pi to pi of the quantity fx sine nx dx, and you put the value of the function, you get 1 upon pi into the negative pi to pi of the quantity x square sine nx dx. We get this quantity, right? Now notice that if you assume this as your function, suppose g of x is equal to x square sine of nx, right? G of x is just a notation, like fx is equal to x square. Since I had used the fx, so that is why I'm using the gx, right? You could have used anything h of x or whatever quantity. So if you substitute negative of x, you get negative x whole square into sine of negative nx, right? This will be x square, and you know that sine of negative x or whatever quantity, I should say theta over here, is equal to negative of sine theta for all theta, right? Which means it will be equal to negative sine nx, which is equal to negative x square sine of nx, right? Which means that this function g of negative x is equal to negative of gx, right? Which means this is a odd function, right? So it's an odd function, so in that case it is going from the same negative quantity to the same positive quantity, which means that its integral will be equal to 0. So we don't need to evaluate this, even this is equal to 0, so our half work is done. Now we have to just evaluate for an, and then we have to substitute the values, and then we have to put a suitable value for fx to get to our answer. So let's see, let me erase this, and then we will be right back. So we evaluated that bn is equal to 0. Now our job is to find an. So let's see, it will be the toughest thing which we have to do right now, but it is not that tough, it is very simple, but it will be like more lengthier than other parts which we have done. Is equal to the value 1 upon pi into the integral negative pi to pi of the quantity fx cos nx dx, right? Substitute the value of fx, 1 upon pi negative pi to pi x square cos of nx dx, right? Very simple, right? Okay, So notice that if you assume g of x is equal to x square cos nx, now when you substitute g of x in the place of x, you substitute negative x, what you get? Your g of negative x is equal to negative x whole square into cos of n into negative x, right? Okay, x square cos of minus negative nx, and remember cos of negative theta is equal to the cos theta, right? Okay, so you get this expression which is telling that g of negative x is equal to g of x, which is an even function. Imagine if it would be also odd function, how easy the life would have been, but it's okay. We still have more things to do over here. We can still apply one property that it will equal twice the integral 0 to pi, so at least we don't need to evaluate for the negative quantity. So let's see. Okay, let me erase this. Okay, so let's write this as 2 times the integral 0 to pi x square cos of nx dx, right? Since it was an even function, right? Now let's solve this using integration by parts, right? You all know that if you have integration u v dv and you assume this as your second function, this as your first function, then you write the first function as it is and you integrate this function v dv minus the integral, you take the derivative of this quantity du with respect to some quantity. Of course it will be with respect to some quantity, suppose x, du by dx dot the integral v dv, and then you will have sorry, it will be dx over here, I'm really sorry, and this is dx. Okay, so this is how you write a function, the product of two functions as this. Okay, you can write it like this, and this is called the integration by parts. Okay, and it will be v dx over here also, sorry. Okay, so this is the relation which we are going to apply over here also. So let's see how the things goes. Let me erase this, then we will solve. So let's leave the constant for now and we are just focusing on this integral. Let's evaluate it. So integral 0 to pi x square cos nx dx, it can be written as you can assume this as your second function and this as your first function. Why? Because you know that if you differentiate this, then it will become 2x, and when you do the second differentiation you will get 1, and which means that you will be only left with the trigonometric function, and which is easy to integrate or find the derivative of, right? That is why it seems much easier to assume this function as the first and this as the second, because you will be differentiating this and you will be integrating this. Okay, so write the first function as it is, integrate the second function. What is the integral of cos x? It is equal to sin x, but remember you have an n, so you need to apply the chain rule by n. Okay, and you substitute it for 0 to pi, right? Okay, minus integral 0 to pi of the quantity, you differentiate this, you get 2x, right? And when you integrate this you get sine of nx dx by n, right? Okay, and notice that when you substitute 0 over here, the whole expression becomes 0, and when you substitute pi over here, notice that sine of pi of n pi is always equal to 0. Why? Because sine of pi, because n is the integral values, so if you put n is equal to 1, 2, 3 or whatever quantity, you will get n is the positive integral, sorry, right, or natural number, which you can say. So sine of pi is equal to 0, sine of 2 pi is equal to 0, sine of 3 pi is equal to 0, sine of 4 pi is equal to 0, and so on and so forth, which means that this quantity is always equal to 0. So this whole expression is equal to 0, and our life became very easy, at least for now. So let's evaluate now this thing. So this integral is equal to negative 2 times 2 by n times 0 to pi of the quantity x sine nx dx. Okay, remember we have this term also which we need to evaluate. After that, we have to multiply by 2 by pi. We have to remember this. So you get negative 2 by n, and again you apply the chain rule, the integration by parts. That is, you will assume this as your first function and this as your second function. Of course, you had a formula for this, but I don't believe in formula much, because how much formula you will learn, right? That is why I believe in methods and the concepts, not in the rote learning thing. Okay, so that is why I'm telling the concepts instead of the formula. The learning of the formula, it's very bad thing in my perspective, to learn the things and then tease them, okay, and to learn and then apply. It's better to learn them conceptually instead of rote learning. Okay, I believe in that. Maybe my point is hated by many, but I don't care about that, because this is my way of teaching. So okay, I'm coming back to my point, because I know many will say that we could have directly applied the formula, because many are because in our colleges and in our schools we are taught like that, because it is like you apply the formula directly, but it's not a good practice, right? We should be working towards the concepts actually, right? Okay, so I'm coming back to my topic. Okay, so this is equal to x. What is the integral of sine of nx? Is equal to negative cos nx by n, right? Okay, and it goes from 0 to pi again, right? Okay, minus the integral, the derivative of x is equal to 1 and is equal to negative of cos nx by n dx, 0 to pi. Now notice that over here, when you substitute 0 over here, okay, let's remove a negative sign over here and let's reverse the limits. What do you say? Is it okay? Yeah. Now substitute the limits over here. You get 2 by n times this quantity. When substitute 0, whole expression becomes 0 because of this x, right? And of course you can take n common from both, so you can write over here n is square, right? You can take this n and this n as common, right? They are constants. So, and when you substitute 0 over here, due to this x, the whole expression becomes 0. And when you substitute pi over here, let's see what you get. Negative of, since you know that upper limit minus lower limit, so this is the negative, so there is, we are doing the minus, right, of n pi, right? And this minus will become plus integral 0 to pi cos nx dx, right? You get this thing? So you are left with, so it will be a negative sign over here, and when you substitute pi, we have to substitute at the place of x also, so that is why it will be equal to negative pi into cos of n pi. And let's evaluate this also, and let's write our final answer. Negative 2 by n into the quantity negative pi cos n pi, right? Plus the integral of this will be sine of n pi by n, goes from 0 to pi, and we had earlier calculated that this is equal to 0. It will be nx, sorry, and this is equal to 0. So we are left with the expression 2 pi by n into cos of n pi, and remember we have to multiply by this, into 2 by pi. Pi and pi gets cancelled and you are left with 4 by n cos of n pi, right? And notice that cos of n pi is equal to negative 1 to the power n. When you substitute n is equal to 1, then you get cos of pi is equal to negative 1. When you substitute cos of 2 pi, it is equal to 1, right? And so on and so forth. That is why you got this. So you got a of n is equal to 4 by n negative 1 to the power n. And now let me erase all this, and we are ready to put all these things in our Fourier series. And let's calculate the Fourier series for x square. So let's find the Fourier series for x square. So you get f at x is equal to a naught by 2 plus the summation n goes from 1 to infinity of the quantity a n cos nx plus b n sine nx, right? You get this thing. And now you substitute the function x square, and let's see. X square is equal to this quantity, 2 by, x square is equal to a naught pi square by 2, right? Obviously this 2 plus what is an? An is this quantity, negative 1 to the power n cos of nx plus what is b? B is equal to 0, so we don't even get this term, right? And this is actually f at x is equal to a naught by 2 plus the summation n goes from 1 to infinity of an cos of nx. This is a general Fourier series for the function fx being even, right? But we will discuss it later in our one shot, so that is why we don't need to discuss right now. Okay, you will get confused if I discuss right now. Okay, so let's solve. X square is equal to pi square by 3 plus you can bring 4 outside, you get summation n goes from 1 to infinity 1 negative 1 to the power n by n into cos of nx. Now put x is equal to pi, right? Why I did that, I will tell later. So when you substitute it equal to pi, you get pi square is equal to pi square by 3 plus 4 times this quantity. Well, let me write it. N is equal to 1 to infinity negative 1 to the power n into cos of n pi, right? By n. I guess it was n square because we had multiplied by that quantity also, right? We had multiplied by 2 by n. Remember that? We had a n square there. Okay, sorry, I'm sorry for that. Okay, so it will be n square over here, right? Remember that I had said that I had taken n as a common, so I had got 2 by n square, and then we had to multiply with that, right? Remember? I am sorry that I could not write n square over there. I'm sorry. Okay, so let's see. So pi square is equal to pi square by 3 plus 4 times this quantity. Well, we had said that it is equal to negative 1 to the power n. So let's see. Let me write this. So we know that cos of n pi is equal to negative 1 to the power n. And negative 1 to the power n into negative 1 to the power n is equal to negative 1 to the power 2n, and it is equal to 1 to the power n, which is equal to 1 for all values of n. Which means this expression is equal to n is equal to 1 to infinity of 1 by n square, and notice that this is equal to this expression, and sometimes in the terms of zeta function we write it as zeta of 2 also, this thing zeta of x, though it is not relevant right now, but I should tell 1 to the power x plus 2 to the power x plus dot dot and so on and so forth. So when I substitute the value of 2 over here, you get this thing, right? Okay, well, it's not relevant right now, so I don't think so that I should tell right now. Okay, so you get you bring this over here, you get pi square by 2 by 3 pi square, right? This pi square minus, let me tell, pi square minus pi square by 3 is equal to 2 pi square by 3. How? You take the common denominator and numerator, I mean you make the denominators as common, so for that you will multiply by 1 and you get 3 pi square minus pi square by 3 is equal to 2 pi square by 3. Why I'm doing such simple calculation? Because so that everyone can understand, because many times people face problem in simple calculations, they are able to understand all the concept but they stuck at simple calculations. That is why I am more worried about the simple calculation than the major part. That is why I did the mistake over there, because that part you know that that will be n square only, but here sometimes people make silly mistakes due to which they come to wrong conclusions, right? That is why, okay, is equal to 4 times this quantity n is equal to 1 to infinity of 1 by n square, and you bring this over here, you get 2 pi square by 12, right? Let me write it like this, 3 into 4, you brought this 4 over here, okay, and you divide by 2 and you get pi square by 6 is equal to summation as n goes from 1 to infinity of 1 by n square. So you get, let me write it over here, you get pi square by 6 is equal to 1 by 1 square plus 1 by 2 square plus 1 by 3 square and so on and so forth. And that is what is written. This is what was proved by Euler, right? So I hope that you all like this video. Then please to like, share, subscribe my channel, and thanks a lot for watching it. Bye bye, take care.